So we'll come to the third part of this chapter on machine design, bolted, riveted and welded joints. The third part will be the riveted joints. So till now we have seen about the bolted joint as well as the welded joints, and we have seen how to design the joints for a given kind of a loading. Now we will see about the riveted joints. Riveted joints also, like the bolted joints, is a temporary joint in the sense that they can be removed at any time of assembly without causing damage to the plates. A rivet is shown here. This rivet has three parts basically. The head is this portion, and the flat portion is called the shank, and the tapered portion is called the tail. So how is this riveting done? Riveting is done for joining two plates 1 and 2. What we do is we drill a hole in both the plates, we bring the plates together, we keep the rivet here, and we have something called a backing plate which is kept at the head of the rivet, and we have a die which has a shape of the same as a head, and the force or pressure is applied on the die plate so that it gets deformed into a shape like this. So you get the same kind of head on both sides after the riveting operation. And the riveting operation can be done at room temperature as well as at high temperature. When the riveting is done at a room temperature, it's called cold riveting. And when it is done at a higher temperature, it's called hot riveting, because it's basically causing the permanent deformation of the rivet. The tail portion of the rivet is getting permanently deformed and comes to a shape of the head. So it's a plastic deformation of the material is taking place. Now the different types of riveted joints we'll see. Basically there are two types of riveted joints. One is called the lap joint and one is called the butt joint. These two joints we have seen already in bolted joints as well as in the welded joints. We'll see how a lap joint looks like. Now we'll see the lap joint. The lap joint is nothing but a joint in which the plates that are to be joined are brought face to face such that an overlap exists as shown in the figure, and then the rivet is inserted in this position, and a die plate is kept in the top of the rivet, and force is applied and causes the tail of the rivet to get deformed into this shape. Thus joining of this plate is done. So if you see the top view, you can see 4 number of rivets along the length of the plate, and this is one single row of rivet. This is a case of single row of rivet. We also have multiple row of rivets. Multiple row riveted joints, that will be more strength joints. And when multiple joints are used, then how to arrange this rivet? You can have a similar kind of a rivet arrangement in the parallel to that, or you can have a zigzag arrangement. So we will see what is a multiple riveted joint. These are the two possible ways of multiple row riveted joints. One is called the difference between the two joint is in the arrangement of the rows. The rows are parallel to each other, as in this case. This is called a chain arrangement. In which the two rows of rivet are parallel to each other. This is one arrangement in which the multiple rows of rivet are in a zigzag manner. It's called a zigzag arrangement. As you can see, the zigzag arrangement will be more efficient because the distance between the two rivets will be lesser, because it will be only this much. So this is about the lap riveted joint. Now we'll see about the butt joints. Now we'll see about the butt joints. One of the butt riveted joint is shown here, in which what happens is the plates which are to be joined these two plates are brought to each other without forming any overlap, and riveted joints are formed between each of the plate and one or two of the cover plates. In this case, only one cover plate is used. These two plates cannot be joined directly, so they are joined to a cover plate which holds both the plate together. Depending on number of cover plates, the butt joints may be classified as, depending upon the number of cover plates, we can classify it into single strap butt joint, and double strap butt joints. The difference between single strap butt joint and double strap butt joint is that in single strap butt joint you have only one cover plate, which is shown here. I'll write this as a single strap single riveted butt joint, because it is having only one row of rivet and only one cover plate. Since it is having one cover plate, it is called single strap. Since it is having one row of rivets in one plate, it's called a single rivet, and this is a kind of butt joint. So if you want a multiple rivet single strap joint, that is also possible. When you have a second row of rivet parallel to this, then it is called a double riveted single strap butt joint. Similarly, if you have another one more cover plate, then it is called double strap double rivet butt joint. So that is a classification of butt joints. So these are the two basic types of riveted joints which you are going to design, and the strength of a rivet is measured by the efficiency of a rivet. Efficiency is a parameter of importance in the design of riveted joints. We will see what is the efficiency of a riveted joints when we come to design of riveted joints. So in this riveted joints, there are some basic parameters which we should be knowing before going to the design of riveted joints. We will see what are these parameters. Now we will see what are the different parameters we come across in a design of a riveted joints. Basically, the parameters are the pitch. Pitch is the distance between two centers of consecutive rivets in a single row. It can be between these two, can be between these two, or can be between these two. The distance between two consecutive rivets in the single row of a riveted joint is called pitch. Back pitch is the shortest distance between two successive rows in a multiple riveted joint. That is between two rows. This is a double riveted joint. The distance, the horizontal distance, or the shortest distance between the two rows of riveted joint is called back pitch of the riveted joint. And we have margin or the marginal pitch. That is a distance between center of a riveted hole to the nearest edge of the plate. The center of a riveted hole to the nearest edge of the plate is called margin. Can be this one, can be this one, can be this one. Any one of this can be called the margin of a riveted joint. So basically that is we have already seen pitch, then we have back pitch, then we have margin. Now we will come to what is the strength of a riveted joint. The strength of a riveted joint is evaluated taking all possible failure paths in the joint into account. Since the rivets are arranged in a periodic manner, the strength of joint is usually calculated considering only one pitch length of the plate. So therefore we should know what are the different possible failure modes of this riveted joint. And based on the failure modes of the riveted joint, we can design the riveted joints. The first failure mode is tearing of the plate. What is tearing of the plate? So the first failure mode of a riveted joint is tearing of the plate. In this case, this is a single row riveted joint. It's a lap joint. When two plates are joined by this kind of, two plates are joined by this kind of a riveted joint, and the force is applied. One possibility is that the plate will tear between the two riveted joints. So if in this case, if the plate is failing between two riveted joints, what will be the tearing area? First we will see what is tearing area. Tearing area, if P is the pitch and D is the dia of rivet, then the tearing area will be P minus D into T, where T is the thickness of the plate. So T is the thickness of the plate, P is the pitch of the riveted joint, and D is the diameter of the rivet. Then the tearing area, that is this area of the plate, is given by P minus D into T. Therefore, what will be the maximum value of force that can be applied? Therefore, the maximum value of force, we will say P1, will be given as ST into P minus D into T. What is ST? ST will be the allowable tensile stress of the material. If ST is the allowable tensile stress of the material, then we have the maximum force which can be taken by the plate is given by ST into P minus D into T, where ST is the max allowable tensile stress of the plate, and P is the pitch, D is the diameter of the rivet, and T is the thickness of the plate. So thus we have the first equation for the tearing of the plates. Now we have the second mode of failure of a riveted joint, that is nothing but shearing of a riveted joint. Now if the two plates are joined like this as shown here, again this is a lap joint, it's a single row lap joint of two plates. In this case of a joint, what is happening is when the force is applied in this directions, the rivet is getting sheared across this cross section. This portion of the rivet is getting sheared. Therefore, we can now tell what will be the shearing area. Shearing area will be the area of the riveted joint, which will be nothing but pi d square by 4. So therefore, we have the second equation, which is nothing but the maximum load which it can take by shear is given by shear strength into pi d square by 4. So there is a maximum load which can be taken by a riveted joint. Now this is the case of a single strap butt joint or can be a lap joint. Now for so this I can write as for single strap butt joint, or it can be a lap joint. Now what about a double strap butt joint? If it is a double strap butt joint, in case of double strap butt joint, you will have one more plate here. So you will have one more cover plate here, two cover plates. It's called a double strap butt joint. In case of if one more cover plate comes here, then there will be two areas of shearing. This will be one area and this will be another area. So in this case, the shearing area will be 2 times pi d square by 4, or I can write the maximum force can be written as SS into 2 times of pi d square by 4 will be the maximum load which can be taken by the riveted joints. So this gives a maximum load in order to avoid the shearing of the riveted joints. This is the second kind of failure of a riveted joints. Next we have crushing of rivet. We will see what it is. Now we have the third failure mode of a rivet, which is nothing but crushing of rivet. If the bearing stress on the rivet is too large, the contact surface between the rivet and the plate may get damaged. That is shown here. When two plates are joined like this is a single row lap joint, lap riveted joint. When the force is applied, what happens is the rivets gets crushed against the wall of the plates. In this case, the contact area, or it's called the contact area or crushing area or bearing area, will be a projected area For all cases where you have bearing area or the contact area or the crushing area, the area should be the projected area in the direction of load. So in the projected area will be, here it will be equal to D into T. Therefore we have the maximum load which can be taken by the joints without any crushing of the riveted joints will be given by SC into D into T, where SC will be the crushing strength of the material or bearing strength of a material. Between rivet and the plate material. That will be the crushing strength of the material. Now the next kind of failure will be the tearing of plate at the edge. The next failure mode, as I have told, is the tearing of plate at the edge. So we have seen earlier about the different parameters in a riveted joint, basically the pitch, back pitch and the margin. So seeing this kind of failure, we can easily understand that if the margin is too small, that is the distance between the rivet to the nearest edge of the plate, if this distance is small, the plate may fail as shown in this figure. To prevent this kind of a failure by tearing of the plate, it is usually recommended to have a margin equal to 1.5 times D, where D is the diameter of the rivet. D is the diameter of the rivet, the margin should be equal to 1.5 D. So that is a minimum condition for avoiding the tearing of plate at the edge. Now we have already seen that the strength of a rivet basically is given by efficiency of a riveted joint. Now efficiency of a riveted joint is given as the ratio between the maximum of P1, P2 and P3, which we have seen earlier, it's not a maximum, it's a minimum of P1, P2, P3 to the load carried by a solid plate. If it is a solid plate, the load carried will be given as the tensile strength of the plate into P into T, where P is a pitch. Therefore efficiency of the riveted joint is the ratio of minimum of P1, P2, P3 to the strength of a equivalent solid plate, PT. In double or triple riveted joints, the failure mechanism may be more than those discussed above. The failure of plate along the outer rows may occur in the same way as above, but in that case the inside row has to fail, then only the outer row can fail. So in that case, the maximum allowable load that the plate does not tear in the second row is given by P4 is equal to ST into P minus D into T, which is the maximum load taken without failure by the first row, plus minimum of P2 and P3. This is the maximum allowable load such that the plate does not tear in the second row. Maximum allowable load such that the plate does not tear in the second row. So these are the different types of failure of a riveted joints. Now we see if these are the different types of failure for riveted joints, how will we design the riveted joints? Okay, now we will come to design of riveted joints. So what is meant by design of riveted joints? The design parameters in a riveted joints are diameter of the hole D, dia of hole, then we have P, which is nothing but pitch of the riveted arrangement, and M, which is nothing but margin. So a given loading condition, how do we finalize the diameter of rivet, pitch and the margin? So first we will see diameter of rivet. or diameter of hole. For this, two conditions are there. If the thickness of the plate T is less than 8 mm, then how do we design this? We find out the diameter of the rivet by equating the crushing strength to the tensile strength of the riveted joint. So this we have already seen. The crushing strength of the riveted joint is given by SC into D into T, and the tensile strength of the riveted joint, sorry, it's not tensile strength, it's the shear strength of the riveted joint. Shear strength of the joint in case of double riveted zigzag joint will be given as pi by 4 d square into SS, which gives that SC into T is equal to pi by 4 d into SS, or we can write the diameter of the rivet should be 4 times SS into T divided by pi into C by SS. This will be the diameter of the rivet or diameter of the hole if the thickness is less than 8 mm, and if the thickness is greater than 8 mm, in that case diameter of the rivet hole is given by 6 times square root of thickness mm, this much mm. So that is about diameter of the rivet hole. And in any case the diameter of the rivet should not be less than the thickness of the plate. And there are different standards which are followed in different industries. Based on that also we can do the design of the riveted joints. So next we come to the second parameter, which is nothing but pitch. How do you find the pitch? Now pitch is designed by equating the tearing strength of the plate to the shear strength of the rivet. Now we have seen the tearing strength of the plate is given by ST into P minus D into T equal to, for double strap riveted joint we know that this is equal to SS into 2 times pi d square by 4. So based on this you can find what will be the pitch of the riveted joint. This is for a double riveted lap joint. For double riveted lap joint, the pitch is given by equating, pitch is always given by equating the tearing strength to the shear strength of the riveted joint. In case of a double riveted lap joint, it will be given by this relation. Then the third parameter which we have already discussed is the margin M. We have also seen the margin M is also critical, in the sense that if the margin is too low, it will cause the failure by tearing of the plate at the edge. So to avoid the tearing of plate at the edge, the margin is usually given as 1.5 times the diameter. So now we will see once again what we have done. So given the thickness of the plate and the load, we can find what is the diameter of the rivet hole by this relation or by this relation, depending upon what is the thickness of the plate. This is the thickness. So if thickness is less than 8 mm, the diameter of the rivet hole will be given by this relation. And basically the diameter of the rivet hole, if the thickness is less than 8 mm, it is found out by equating the crushing strength of the rivet to the shear strength of the rivet. Based on your riveted joint design, you can do this equation, equating the crushing strength and the shear strength, and you can find what will be the diameter of the rivet hole. In some cases, when the thickness of the plate is much larger, it's greater than 8 mm, then the diameter of the rivet is given by 6 times the root of T mm. So thus we get what is the diameter of the rivet hole. Now once we get the diameter of the rivet hole, the second parameter will be the pitch of the rivet hole. That is a distance between two rivets in a consecutive rivets in the single row of a riveted joint. Now that is found by equating the tearing strength of the riveted joint to the shear strength of the riveted joint. By equating these two, once you know, because you have already found out what is the diameter of the riveted hole from the above relation, and SS and ST are nothing but the shear strength of the material of the rivet and the tearing strength of the material of the rivet, material of the plate. So knowing these strength values, and thickness of the plate is also known, and D is the diameter is also known, so only unknown will be the pitch of the plate. So this way we can find what will be the pitch of the riveted joint. And the third parameter will be the margin of riveted joint. Once the diameter of the riveted hole is known, we can find margin as 1.5 times the diameter. So this way we can do the riveted joint design. Now we'll try to solve some problem and see how we can apply these design principles. Okay, now we'll try to solve one problem. A single riveted joint of 6 mm plates with 20 mm dia rivets having a pitch of 50 mm, the tearing resistance of the plate. So what will be that? We'll list out what are the parameters which are given here. So we have the thickness of the plate is given as 6 mm and diameter of rivet is given as 20 mm. And the pitch of the riveted hole is given as 50 mm. And they have asked what is the tearing resistance. So what will be the tearing resistance of this? You know, tearing resistance P1 is given as ST into P minus D into T. So what will be ST? Sorry, in this case they have given ST, or the tensile stress in plate, is given as 12 kgf per mm square. If this is given, we know that P1, the maximum tearing resistance of the plate, is given as ST into P minus D into T, where ST is the tensile stress in the plate, P is the pitch of the rivets, and D is the diameter of the rivet, and T is the thickness of plate. So in this case it will be how much? 12 into, what is P? P is 50 minus D is 20. We'll keep the units in mm only because we have the tensile stress in kgf per mm square. So we will get the resulting answer also in kgf. Into what is thickness? Thickness is 6 mm. So what will this give? This be? It will be 12 into 30 into 6. So this will be 2160 kgf. This will be a tearing resistance in the plate. This is a simple problem. It's a direct application only, but you should know that which first of all, whenever you are given a problem, it's always better to list out what are the parameters which are given, and also the parameter which you have to find out. Then you can write out what is the relation connecting the unknown parameter and the known parameters. Then you can go for substitution. Now we will see another problem. The force required to punch a hole of 20 mm dia in a 5 mm thick plate with UTS of 250 megapascal is what? Now when you are punching a hole of 20 mm diameter, so it's not 20 meters, it is 20 mm. When you are punching a hole of 20 mm dia, so I will draw it like this. You're punching a hole of 20 mm diameter on a plate of thickness 5 mm. This is 20 mm dia. So if this is the case, what is actually the shearing area in this? In this case we have to find what is the force required. So we are given the UTS value, so only we have to find out what will be the shearing area. In this case, can you tell me what will be the shearing area? So just try to visualize the problem. You have to make a hole in a plate. So when you are punching, how you are getting the material to be sheared? You are shearing the material along the circumference of the hole. Therefore, shearing area will be this area. And what will be this? It will be the perimeter of the hole or circumference of the hole into the thickness. So the shearing area in this case will be pi d into t. So this will be pi into 20 into T will be 5 mm. So what will be the force required? Force required will be UOTS value into the shearing area. That will be 250 megapascal is nothing but 250 into 10 power 6 pascals into the area is 20 into 5. Since the Pascal unit is in Newton per meter square, we will convert this area is also into meters. So millimeter, when you convert to meter, you have to multiply by 10 power minus 3. Here there are two dimensions, 20 and 5. So this becomes 10 raised to minus 6. So what will this be? 250 into 10 power 6 into pi into 20 into 5 into 10 power minus 6. So this will be 78,539.8 newtons, or I can write this will be equal to 78.54 kilonewtons. So this will be the force required to punch the hole of diameter 20 mm in a 5 mm thick plate. Now we will see another problem. Now a bracket is rigidly mounted on wall using 4 rivets shown here. Each rivet is 6 mm in diameter and has an effective length of 12 mm. Now direct shear in the most heavily loaded rivet will be what? Now which will be the most heavily loaded rivet in this? We know it will be the top 2 rivets will be the most heavily loaded rivet, and the eccentric loading of rivet is the same as the eccentric loading of bolted joints. So that we will not be discussing here because it is already discussed in the bolted joints. The only difference is you have to find the resultant maximum shear in all the joints, and you have to design the riveted joints to take the maximum shear, which will be the resultant of a direct shear stress as well as a secondary shear stress. The direct shear stress will be caused directly by the load, and the secondary shear stress will be caused due to secondary shear stress or the normal stress may be caused by the torsion or the bending. In this case, the secondary will be a normal stress which will be caused by the bending of this plate. When you apply 1000 newtons here, in each rivet you will have the direct shear here and a normal stress. This will be given the bending stress. Therefore the resultants will be what? Resultant will be given by the principal stress, because one is shear, one is normal. Therefore the resultant will be given as square root of sigma square plus 3 tau square. So in this case we are not bothered about that. We are only asked to find out what will be the resultant, the direct shear in the maximum heavily loaded rivet. So if these are the heavily loaded rivet, what will be the maximum direct shear? What will be the direct shear given by? We know that when a load 1000 Newton is acted, how we solve this problem? We shift the load 1000 newtons to the centroid of these joints, and also which will be given by the load as well as a moment in this direction. So what will be the direct shear stress in the lower joints? Direct shear stress will be the load by the stress caused by the load directly. Therefore direct shear stress, I can write it as direct stress in all the riveted joints will be the same, which will be given by the direct shear, the load acting on it will be 1000 by 4. Therefore the shear stress will be given by the force by the shearing area. This will be 1000 by 4 is 250 newtons. Therefore 250 divided by pi d square by 4, where what is d? The diameter of the rivet is 6 mm, so I can write it as 0.006 square divided by 4. So what will this be? 250 divided by pi into 0.006 square divided by 4. This will be 8841941.28 pascals or Newton meter square. This will be equal to 368.8 megapascal. This will be the direct shear in the most heavily loaded riveted joint. And see this, the question is very simple, and this question was asked for GATE 2010. So it's a just application. Once if you know the concept, you can easily find out what will be the direct stress that we have seen here, and you can easily score the marks. And this was asked in the GATE 2010. And as I have already told you, the riveted joint design is almost same to the bolted joint design. Therefore, the problems will be quite similar. Eccentric loading of riveted joints will be same as the eccentric loading of bolted joints. So once you know the concept in bolted joints, you can apply the same concept in the design of riveted joints also. With this, we come to end of the design of riveted joints, and also we come to the end of this third chapter on the design of riveted joints, bolted joints and welded joints. Thank you.